this case, we're going to be falling, and it's under the umbrella of mechanics. And in this case, the resistance is actually proportional to the velocity. So our minion is actually falling this time, okay, rather than rising. And you can see here I've got some forces actually on the minion. He's being resisted, kV, and gravity is acting in his direction, or the direction he's falling. Okay, let's have a look. Okay, I'll try and get the pen. See if I can draw a big one. Yes, okay. Here we go. Alright, so what do? Well, we set our forces up. Now, if you have a quick look over here, kV is acting in the opposite direction to motion. Motion is actually, he's going down, he's falling, so it's just basically the drag or the resistance kV is actually negative, and the mg and the net force is actually, which is the balancing of these two forces, is in fact mx double dot, which x double dot hopefully we know is acceleration. Mg is acting downwards again, and mkv is the actual force which is acting opposing motion, I guess you could say in this case. So really, when we divide by m, you can see here we just get the equation of motion, which is the acceleration equals g minus kv, or x double dot equals g minus kv. Now, we're going to, because we can rewrite acceleration a few ways, we're going to be using the different variations dv dt and v dv dx, and we may even sometimes use the fact that velocity is dx dt here and there. Okay, so what did we do first? Well, we just rewrite acceleration as dv dt equals g minus kv. We can actually separate the variables. This may sometimes require taking reciprocals of both sides, but in this case we just multiply. Let's have a look. We're going to need to, yes, move the g minus kv over to the left and the dt to the right. Then we integrate. You can see here, let's try and make it a little bit bigger. And here we are. Okay, so we integrate from 0 to v and dv and 0 to t dt, which is going to give us t obviously down here, and it's going to be let's see here, it's a log. So we now have t is equal to 1 on k log g minus, or sorry, g over g minus kv, multiplied by k. Take the exponentials of both sides. As you know, logs and exponentials are inverse functions. That's why the ln disappears, and we end up getting an expression with v in it. Eventually we need to rearrange it. We can get here the v is equal to g on k brackets 1 minus e to the kt. Now we can see if t goes to infinity, e to the minus kt will go down to 0, and we'll get what's called the terminal velocity. And we're going to look at a different way to get the terminal velocity later on. Okay, so now we've just got the function. You can see here that the actual velocity is a function of time. Okay, so let's actually now have a look at the displacement as a function of velocity this time. So I'll try, let's see if this pen, I'll try and get the pen, let's see if it's, it might work. Okay, alright, let's make it a bit bigger. Okay, alright, so what do? Well, again, we write the forces down, the net force x double dot equals g minus kv. Now we use the v dv dx instead of the dv dt, and we, in this case, we just well, divide both sides by v. Separate the variables, we have to take the reciprocals of both sides, but basically we separate the variables, and then we need to look at that fraction, v over g minus kv, and see many times that g minus kv goes into v. Well, it goes in minus 1 on k times, and there's a remainder g on k. Now, so we basically need to solve this integral, and we've actually had to do polynomial division, I guess, and this is what happens here. We end up getting that x is equal to the integral from 0 to v of minus 1 on k plus g over k all over g minus kv dv. And you can see here this is going to turn into a log. I'll just make this a bit bigger, so it's a bit small here. Okay, so here we are. And you can see here it's just a log, and here we have now our x as a function of velocity. Okay. All right. Sometimes we need to get x as a function of t. We'll just have a look here. This is the how we get x as a function of t, and we're going to need. Didn't seem to do it that time. I'll try over here. Ah, there we are. Okay, let's make it a bit bigger. Okay, here we go. From earlier we had that the v was equal to g on k 1 minus e to the minus kt, and we rewrite the v as dx dt, and then we basically need to separate the variables and integrate. So we integrate dx from 0 to x and g on k bracket 1 minus e to the minus kt dt from 0 to t. And you can see here we can get x as a function of t eventually down here. X is equal to what? We can take the g on k squared out of kt plus e to the minus kt minus 1. Okay, so that is now x position as a function of time. Now, the last little thing is just wrote a little bit on terminal velocity. So when we're actually falling, we basically reach what's called a terminal velocity, when the net force is balancing. Basically, the gravity is equal to the resistance force. You get what's called a terminal velocity. Now, over here, you can actually see there's I've got a diagram from a physics situation where you actually have a look. I'll just see if we can. Okay. I'll have a look. This is the parachute situation. You can see here the person will accelerate if they're jumping out of a plane, for instance, to about 50 meters a second, and then basically they reach what's called terminal velocity, which is about 180 kilometers an hour. Then they open their chute at about 40 something seconds, 42 seconds, you can see there, and the chute obviously decelerates the parachutist down to about 8 meters a second. And the only thing is 8 meters a second is still about nearly 30 kilometers an hour, so you're going to be hitting the ground at about 30 kilometers an hour. But I mean, that's much better than hitting the ground at 180 kilometers an hour. And that's why I guess they always say wear a parachute if you're going to jump out of an aeroplane. Okay, well, thank you for watching, and bye for now.